For years, the artificial intelligence industry has operated on a single powerful belief. Bigger models mean smarter models. We have poured billions of dollars into scaling parameters and feeding more data into large language models. The expectation was that if we just kept adding compute, we would eventually reach artificial general intelligence. But recent research suggests this path might be hitting a wall. It turns out that intelligence in these systems is not building forward as we assumed. Instead, it is learning backwards. And this fundamental flaw implies that the scaling hypothesis has hard boundaries. For senior systems architects, this is not just a theoretical curiosity. It is a practical stress test for your return on investment. Here is the thing. When we train a model to recognize a relationship, it does not learn it symmetrically. Consider a simple fact. If you tell a model that Paris is the capital of France, it learns that association. But if you ask it to identify the capital of France, it often struggles. This is known as the reversal curse. The model trained on A is B cannot reliably infer B is A. This directional asymmetry persists regardless of how large the model gets. You can double the parameters, you can quadruple the data, and the gap remains. This suggests that simply throwing more compute at the problem does not resolve fundamental logical gaps. It implies that the current forward-only training paradigm is suboptimal for developing robust intelligence. Now consider the implications for system design. If you are building a production system where logical consistency matters, scaling alone is insufficient. We are seeing emergent abilities in large models that may be statistical mirages resulting from scaling laws rather than genuine reasoning. This indicates that the current scaling hypothesis has diminishing returns. To understand where the boundary lies, we need to look at a new framework called reverse thinking. This approach challenges the standard method of training. Instead of only feeding problems to the model, we train it to reason from solutions back to problems. Experiments with this bidirectional approach have shown promising results. Models trained with reverse thinking demonstrated a significant improvement over standard zero-shot baselines. More importantly, they outperform standard fine-tuning using only 10% of the data. This highlights superior sample efficiency. It suggests that the direction of learning matters more than the volume of learning. If you are an architect evaluating whether to invest in a larger model or a better training strategy, the data points toward the latter. Purely statistical approaches are insufficient for AGI. Future breakthroughs likely require neuro-symbolic integration or explicit reverse modeling to overcome the fundamental limitations of current large language model architectures. Let us dig deeper into why this matters for your engineering decisions. Think of it like learning a new language. If you only memorize vocabulary lists where English words map to French words, you might know that apple equals pomme. But if you are presented with pomme and asked for the English word, you might not know it. This is the reversal curse in action. It is not a memory failure, it is an architectural bias. The model has learned a specific path through its neural weights but has not generalized the relationship in both directions. Scaling the model expands the map, but it does not change the direction of the path. This brings us to the concept of epiplexity. This term suggests that generalization depends more on strategic data curation than architectural scaling. It is about the density and quality of information rather than the sheer quantity. For a systems architect, this is a critical shift in mindset. You stop asking how many tokens can we process and start asking how do we structure the training data to force bidirectional understanding. If you continue to rely on the scaling hypothesis without accounting for this directional bias, you risk building systems that fail at the most basic logical inference tasks. You might have a massive model that cannot reason about the inverse of a fact it was explicitly taught. The RevThink framework offers a concrete solution. It introduces reverse thinking into the training loop. By forcing the model to work backward from a solution, we create a more robust reasoning capability. This is not just about getting a higher score on a benchmark. It is about building systems that behave more like human reasoning, where understanding a concept implies understanding its relationship in reverse. A human who knows that water freezes at 0 degrees also understands that 0 degrees is the freezing point of water. The model should too. However, there is a key knowledge gap that remains. We do not yet know if current models can fully overcome the reversal curse without explicit reverse training. It is possible that the scaling hypothesis is fundamentally bounded by these directional learning constraints. If that is true, then a paradigm shift is necessary. We must move from pure scale to bidirectional intelligence. This means that for the next generation of systems, the engineering focus will shift from buying more GPUs to designing smarter training pipelines. This shift has immediate cost implications. If you can achieve better reasoning performance with 10% of the data using reverse thinking, the cost savings are substantial. You are not just saving on training time. You are reducing the inference load because the model is more efficient. It does not need to hallucinate or guess as often because its internal logic is more consistent. For a senior architect, this is the difference between a system that works and a system that scales gracefully under pressure. In the end, the lesson is clear. Intelligence is not just a function of size, it is a function of how that intelligence is constructed. The reversal curse reveals a critical failure in our current approach. It shows that we have been building houses on a foundation that only works in one direction. By incorporating human-like reverse logic, we can enhance reasoning capabilities significantly. We can improve sample efficiency and reduce the need for massive datasets. While RevThink demonstrates that incorporating reverse thinking enhances reasoning, the research argues that scaling alone is insufficient to fix this intrinsic architectural bias. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.